Thank you. Sorry for the delay. We are a bit late with the room problem, but we fix everything. So now I help me to introduce you. Professor Michalis from New York University is.
Don't need all of it.
No, I don't read of it. He's a professor of electronical and computer engineering here in New York University. It's a bit that you are here, right?
It's been 10 years.
10 years now. Oh, no. And before he had the PhD in Yale, right? Jail. Never able to say code. And today we speak about two of us, software and hardware for design for FHE ASIC accelerators. Thank you very much.
Thank you, Chiara. Thank you for the kind introduction. Hi, everyone. Sorry for the delay. Trust me, I wasn't responsible for it. So I asked Chiara whether she give a brief introduction to FHE, and she said you should. So I'll be doing that. So the people who already know the stuff, bear with me for a few minutes. It won't be long. People who don't know, maybe you learned something today. But I'll go quickly through that so we can focus on the essence of the presentation. So quickly about the motivation behind this work is on data protection and privacy, right? This is the main focus of my research, and I understand this is the main focus of the research of many people in this audience. So data data exists in three different forms, right? Abstractly, one is data in transit, which is the typical use of data we've seen, right? That you have some, for example, you talk to the internet, and then you send something to Facebook, to Google. The communication in between is encrypted. So when the data leaves your computer, gets encrypted, it travels through the internet in an encrypted way, arrives to the other side, gets decrypted, and gets processed, right? So that's the data in transit problem, and to some extent it's a solved problem. We have RSA, we have authentication, we know how to do key exchange. So in some way, again, when data is in transit, then we have cryptographic guarantees that it is working as intended, that this privacy is preserved. The second form of data, how data exists, would be data at rest. That means when they're stored in a hard disk, right? What kind of attacks can exist there? Well, someone can take the hard disk out of the computer and try to take the data from there directly. We kind of almost solve this problem. For example, you can do encryption at the hard disk level. So whenever you add something to the hard disk, it gets encrypted. So if someone takes the hard disk out, there's nothing they can do with the data without having the key. And the last form that we use data is actually data in use, actually when we actually compute on the data. And for the FHE people, it's natural, right? This is what we're discussing all these years. But this is not a solved problem. And this is why, well, many of you are here, I'm here too, because we've been working on this problem. So data in use means, again, when the data arrives at the destination, the endpoint, it has to be decrypted to be computed on, right? That's how modern computation works. And the problem here is that once the data gets decrypted, there are very many ways that the data can leak, that your privacy will be breached. The two main categories would be either the host themselves is malicious, so they have your data and they use it for other purposes than intended. It could be picking into data. Facebook, for example, has
They not see the slides.
They're not, but no. Someone said they see, right?
Yeah, I was seeing your slide. So
why?
I can check it.
Yes. Let me try this.
If it's recorded, I guess.
So you can go on.
Yeah, someone said they can see the slides, right? So could be the person's issue. Yeah, could be something temporary there. So what I was saying, that once the data gets decrypted, it can be seen, and there could be two ways. Again, our privacy can be breached. One, the host is malicious, so they're trying to look at the data for financial gain. Again, Facebook, Google have financial incentives to look into our data and make money out of our data. Or it can be some kind of law enforcement agencies that have some interest into looking at the data without the consent of the user. The other way of our data getting leaked is vulnerabilities, right? So even if the host is not malicious, still it's a computer with problems, right, with vulnerabilities. It can be at the lowest level, at the hardware level, like we've talked about hardware trojans. We may not have seen them in practice, but there's always, people are afraid that the hardware can leak information. We've seen though macroarchitectural side channels, spectral meltdown, the ones that brought this into our attention. So these are ways to take data out of the computer and steal the data. And then as you go up the software level, there are 0 days coming up in the operating system level, or at the application level, you have either intentional backdoors, or you have bugs like Heartbleed that enabled slowly data to be taken out of memory byte by byte, right? So all these things here on this slide proves that once the data gets decrypted to be used, it can leak, either in a malicious way or in an accidental way. So that's what will motivate it here. So there's a lot of interest and research on this. One line of work will be somehow to enforce trust through hardware. SGX is an example of a commercial product. SGX, who have seen many attacks to SGX and how data can actually leak from SGX at the end. Trust Zone is the ARM solution. There are many academic solutions from many universities around the world that have been proposed. So you either do hardware isolation and enclaves, or you try cryptography, right? You try protocol solutions, multi-party computation is one. Homomorphic encryption, to some extent, is a primitive for multi-party computation, right? Functional encryption and other techniques that don't rely on hardware, but rely on mathematics. So you can approach it again 2 ways. Either you trust the hardware, or you trust math. And the trust in the hardware actually hasn't been proven to be very okay, because all these things have leaked, and we have a lot of papers on it. With math, we'll be doing great work because of the mathematicians in this room and all around the world. So to some extent, right, hardware has not been proven to be very secure in terms of isolation, but mathematics have proven to be giving great solutions. So this is where we come in, and again, many people in this room, where we're looking into never decrypting the data, right? Once again, the data gets decrypted, it can be leaked one way or another. And hardware doesn't help much. It helps to some extent, depending on your threat model, but it's not foolproof. So the blanket protection is never decrypt, always manipulate data while the data stays encrypted. So even if you steal the data, there's nothing you can do, right? You have your Heartbleed takes bytes out of memory while data is encrypted. You have 0 days, you can access memory. You have microarchitectural leakage from Spectrum Meltdown. You take the data, there's nothing you can do with it unless you have the private key to decrypt the data. Very quickly, homomorphic encryption allows you to meaningfully manipulate data without decryption, which is exactly what I'm trying to say here. Very, very primitive example. You have 5 and 7, you encrypt, and you have 2 ciphertexts that you don't know what they are. You can still meaningfully manipulate the ciphertext through some operation. You get a result back that when decrypted, it responds to an operation that could have happened in the ciphertext. In this example, it corresponds to addition, right? So you can do, for example, modular multiplication here, and that is homomorphically equivalent to addition of the payments. So when the operation happens at the endpoint, right, in this scenario, whatever you leak here, there's nothing you can do with it, because unless you have the key to decrypt, you steal 49, nothing what you can do with that, right? So that's the idea. So when you have untrusted endpoints, have the data always being in a format with fully homomorphic encryption, which cannot be leaked. There's some applications proposed. We'll see the challenges of applying FHE, but some of them are actually being piloted to real life and real applications. The main one is done about a week is the genome-wide association studies for genomic processing. Smart grid also some things we've seen, and the others are examples of private set intersections where you have different parties trying to compute on common data, but they don't want to share their data. Again, MPC has also solutions to that. Very quickly, for people who think that homomorphic encryption is magic, well, it's magic to non-mathematicians and to me, who I'm not a mathematician. But a very, very simple example just to motivate how homomorphic encryption works. Pallier encryption works this way, where the message is being encrypted as the exponent of the number, and then you have some randomness factor added and modulo some kind of a field. So you have the encryption to be, again, the message being in the exponent. So, for example, if you're to multiply 2 encrypted, so that's the encryption, right? If you're to multiply 2 ciphertext, you notice quickly that the messages actually are getting added, right? So when you multiply, because the base is the same, you can the multiplication of the exponent leads to the addition, multiplication of the numbers leads to the addition of the exponents, since the base is the same, and you have surrounding constructor, so you see the result is essentially the addition of the two ciphertexts, right? That's really homomorphic encryption. So I computed only on ciphertexts. Still, internally, in the plain text level, I had addition. So I multiplied the ciphertext and I got additions from the plain text. That's roughly the idea of homomorphic encryption. What I showed now is example of partial homomorphic that you can apply only one operation in the ciphertext. That was addition, the example I showed. There are other schemes. RSA, interestingly, is homomorphic also. It's multiplicative homomorphic. And there are the other ones that are used. They're not heavily used. And then you want to expand this, right? Because only having additions gives you a very limited set of algorithms you can employ. So you want to go past that, and you want to expand it a bit to be able to do more meaningful computation. Because only additions have a few interesting applications. One is smart grid data aggregation. So when you aggregate data, you're just adding them up. So it can be used. And the other is e-voting, because when you vote, you again aggregate data. But other than that, no other algorithm can be supported by just adding numbers. So you want to have an orthogonal operation to addition, in this case, where multiplication can make a difference. And the idea of somewhat homomorphic came before fully homomorphic, that you have a lot of additions and one multiplication. So you kind of expand the computational complexity of your algorithms. And nowadays, since 2009, we have the idea of fully homomorphic came into reality, into fruition, where you can do addition and multiplication unlimited number of times. So in theory, you can support any computation. In practice, that never happens, right? So there are many challenges we need to solve, and the major challenge we need to solve is performance. So once you have something working in plain text, you convert it to a corresponding computation in ciphertext, it becomes extremely slow. How slow? Well, that slide I have here is taken from the DARPA DEPRIVE program when it was first announced. So the program actually will participate, and NYU participates as one of the teams that got funding from DARPA to work on this. So the idea is that it's currently accepted to be 9 orders of magnitude slowdown. It's kind of 6 to 9 roughly, and in some way the unencrypted version, well, 6 actually, that's what it shows here. That's for CNN, right? CNN training, yes. So CNN training with unencrypted takes that amount of time. FHE makes it 6 orders of magnitude slower. And the idea of the program was to bring it down to 10 times slower than unencrypted, which is, I'm not sure how close we'll get there, but we're lowering the orange bar, right? So essentially what I'm here to discuss is how we can bring this down as close to CPU performance as possible. But that's, for the people it's a very difficult problem to solve. And that's why in this talk, what I'm trying to do is to discuss the problem from 2 fronts. One from the software side, one from the hardware side. Because innovation, novelty, research can come on both ways, right? You can have algorithmic improvements and you can have hardware improvements to be able to accelerate fully homomorphic encryption. So with that, let me give a minute. Are there any questions? So I try to motivate FHE, the need for FHE, why FHE is slow and why we need acceleration. Any questions?
I have a question.
Yes.
From the chat.
All right. Also check.
Okay, I can read it.
Okay, I can see. So does it make sense to use FHE in edge devices, or is it only for outer servers who mostly don't use the information? So the question of sense can only be answered by how much performance degradation you can accept. Because if FHE was free, everybody should apply it. But it's not, right? So the answer to your question is, can we accept the overhead? And I think for real-time critical devices, that such as even routers, actually, it may be impossible to employ FHE. So I don't see, even though I did mention the word endpoints, and you're right to point it out, I cannot see FHE being employed in real-time requirement devices, but I can see employed in specific applications where privacy of the data is really important. For example, genomics, or things that if you lose your privacy, it can lead to big problems for you financially or even health issues. So the answer is I don't think homomorphic encryption will ever be applied to anything that's low in computational resources and has real-time requirements. That's my belief. I hope I'm wrong. All right. So first part, I'll talk about some of the work we've done in my lab on the algorithmic side of accelerating fully homomorphic encryption. Because at the end, what I'm trying to motivate here, both have to go together. The hardware has to be created for the software, and the software has to be created for the hardware. That's the co-design idea I'm trying to promote. I don't have results to show on co-designing. That's the title I've added the word towards. It's work in progress, but we're trying to approach the problem. Both sides at some point will meet and we'll say, okay, the software will be changed this way to support the hardware, and the hardware has to be developed to support the software. So they both have to go together. So on the software side, so fully homomorphic encryption, right? Besides the schemes themselves, you can think of computing with FHE using two very distinct ways. One would be with modular arithmetic, and one is bit-level arithmetic. Probably for some, it should be easy to understand what we mean. Again, think of when you add two numbers, right? You add 5 and 7. In modular arithmetic, you just add them and you're done. When we talk about bit-level arithmetic, 5 has to be converted to bits, and then you have bitwise addition of the bits. Clearly, there's a performance difference. Modular arithmetic is fast, right? Because you work on integers and you do one operation. Bit-level arithmetic is slow because you operate on gates per bit. So the same addition, if it's 64 bits, it will take you at least 64 gates plus in order to do the same operation in bit level. Why would the bit level be preferred though? What the property that makes me have it on the slide? Where is it better than modular arithmetic? It's not a test, I'm trying to engage you. Like my students, right? I know when they're starting to sleep, I have to ask a question. Well, the answer is the expressivity of the computation. With modular arithmetic, you can essentially add and multiply only. But with bit-level arithmetic, actually, because you have gates now, gates, if you have a NAND gate, you can do any computation. That includes comparisons, right? So many times, for example, with modular arithmetic, you cannot do A greater than B. It's not an operation you can perform with additional multiplications. But if you convert everything to bits, the comparator is a Boolean circuit, right? And you can actually use it. Is there a question? Right. Or internal inside joke?
It was an MPC-based private comparison.
Okay. Yeah. So you know.
I had an issue with that thing. Yeah.
You have an issue with this?
No, yeah, with the limitations. I think you could perform comparisons only using additions and multiplication. I don't see why you wouldn't.
With any integer addition multiplication, right? And you have a comparison, and what is the result is encrypted. How can it be used for the comparison? So, I mean, in bit level, we understand it stays encrypted, right? And we use its 0 and 1 to multiplex results, and we keep things inside. We can talk about it, right? Yeah. So anyway, what my point here is that actually what we've been trying to do in the lab is to take the best of both worlds, right? And we published a paper recently in ICCAD with a technique we call bridging, where we convert from one type to the other. So either from bit level to modular to bit level. They're asymmetric in complexity, the conversions. But in this way, you can have your computation being modular arithmetic as much as you can because it's fast. And when you do comparisons, you can convert your data types to bit level arithmetic so you can do your actual comparisons.
Do you use any existing modular to arithmetic or conversion schemes from crypto, or do you have your own?
We have our own libraries built for this. Actually, we have a framework we call E3, and this is the reason I reached out to Chiara, because she cited us. And I saw the paper from TII. I said, okay, we should talk. So we have a framework that we have built the primitives ourselves for modular arithmetic and for bit-level arithmetic.
And it allows for conversion between the two.
It does, yes. And it's open source, so you can use it today.
In terms of performance overhead,
The performance already depends on the conversion, which way you go, right? From bit level to modular, modular to bit level, there's a big difference between those conversions.
And is it scalable in terms of
It's infinite, but the overheads add up and make it impractical if you keep converting between the types. So you should, in practice, you should only convert once to have a practical setting. Otherwise, if you keep converting, the overheads are tremendous. You should just stay to one, actually bit level, the comprehensive one, right?
my question is not specifically from FHE, but from a more generic, let's say, crypto.
Let me clarify, I'm not a cryptographer,
No, I.
but yeah, well, my expertise is hardware and algorithms. So on the crypto side, I'm trying to avoid speaking too much. Like I say, something stupid. But we take FHE ASICs, right? We don't really touch it. So, but we know the operations are given to us, which is evaluation of addition, evaluation of multiplication. So we're trying to work with those two. So what we have done here, we have built a framework. Well, how the framework expanded with this bridging idea that it has different data types for modular and bit level arithmetic. And actually, well, that's what the framework E3 does. So you type in C++ and automatically the data types are being converted internally to FHE types. And then the operators are being overloaded to support the addition. Well, here there's comparison, there's multiplication, there's addition. So in some way, the secure unit, which is the bit level arithmetic, will be cast automatically by the framework, secure mode, and then the multiplication will take place. There are actually a few more data types in place because it's not worth to have Boolean arithmetic being many bits besides one. So we added a secure bool data type as well in order to be more efficient in some of the computation. So an idea, when you do a comparison between secure ints, you get back a secure bool. And then this can be used to multiply with the secure int. This is much faster than multiplying secure mod to secure int because one is 1 bit and secure int is actually as many bits as what you have defined as your maximum range. As you can understand, the range here is important. In regular computers, we very easily say 32 bits, 64 bits. It's the same. Here, every bit you add adds performance overhead. So if you can constrain, for example, to 8 bits your computation, then that's great, right? Even 9 bits, right? If you don't need 16 bits, don't round it up. Stay to 10, stay to 11 bits, because every bit added makes a big difference in performance. How strict is so should I finish by noon? I should, right? I mean, okay. Well, we started 12 minutes late. Anyway, so there's, I mean, the paper has the information about the conversions. I'm not sure if, it's, we should discuss them more. I think what's more interesting here is the application, and then individually, if someone is interested, we can discuss also the technical content of the conversions. So I always like to give perspective to this, right? Because it's, with techniques, well, why do we care? We have an application that where bridging turned out to help us make it practical, and that's genotype computation application. So that's actually part of the IDAS competition that, I don't know if you know of it, it's actually genomics privacy competition. We participated twice with some good results, but it's, well, tough to get first place in these competitions. We've been going down the ranks every year we participate, so we stop now. There are companies that do this, professionally now, right? There are many companies that do FHE, MPC, and there are people who do it out. My PhD students do it for a few weeks. We can't compete with people who do it full time. So it ended up not being productive for us anymore. But we participated twice, we learned a lot. The first competition was about genotype computation, which gives some good perspective why FHE can be very useful. So when we have our DNA, right? Our DNA is unique and should be kept private because it has a lot of information that once it leaks, it can cause us some problems. For example, there's this doomsday scenario in the US that health insurance companies can be looking at our, for example, predisposition to cancer based on our genomic data. And if it seems that we're more prone to getting like prostate cancer or breast cancer, then our premium will be 10 times more because at some point they have to treat us for cancer and they know that. So if they have access to our genomic data and they see the predispositions, then they say, okay, you have to pay $1,000 a month. You have nothing, you pay $10 a month, right? So you understand why privacy is a problem. However, we still need our doctor to give us this information, right? We want our doctor to say, you may have prostate cancer in the future. Please be careful. Please get tested every year. Please eat properly. Please do this, please do that, right? So we need the answer, but we want the answer to be known to any other party. So when we sequence our DNA, actually DNA sequencing is a very stochastic process. Depending on the mode, the way, there are a few ways to do it. The most popular way would be to, you have a machine that, again, I'm not a biologist or a genomicist, so they say things at a very high level that could be wrong. But roughly the idea is that you have your SNPs, you have your bases, and you enroll your DNA, and then there's a pool of stuff, and you put bases that have different luminosity. So A has some luminosity, C has a different luminosity, D has different luminosity. So those things get attached to your DNA, and actually you read images, and by the luminosity, you can understand which bases got attached to what, and you can actually read the sequence of the DNA. Very, 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 very high level speaking, right? Illumina does that. Well, that's also the name of the company. It comes from the technique they employ, which is luminosity-based understanding of our genome. So when we do that, because we cut the DNA into different pieces, not all of them will get things attached meaningfully for us to fully understand the whole genome. So many times what we get back is actually only a subset of our genome we can read, not all of it. However, our DNA is actually very well correlated, right? So between humans, I think 99% is common DNA. So actually, since we have the human genome proxy, we have a reference genome, the missing parts we can complete by looking at the reference genome. And the correlations between our, again, genomic data that if I have ACG here, then I have ACG there too. So these correlations allow us to complete the missing pieces by looking at what we have already. As you understand, to do that, actually that's a process of imputation, genotype imputation, that when we have question marks that we haven't understood what the base is here, then we know, okay, since this is 2, 1, and 0, and this is 0, 2, and 0, definitely the missing piece should be 2, because they're correlations that we know. So that's the idea of genotype imputation. As you understand, it's important for this to be done in a private way, because at the end, our genome comes out. And we don't want the service we're using for imputation to know what our genome is. We still need to get the data out. So we have a paper in Cell Systems that we discussed the way we do it. It's it's not so much machine learning, it's more information theory based, that we try to extract correlations, and then we actually computed correlations, and we made decisions based on correlations. But what I wanted to point out is the performance that the technique I showed, the bridging technique, gave us. So from the left side, you see bridging enabled, not the different encryption parameters. Of course, the bigger the encryption parameters we have, the more data we can compute on. And you see that for the data sizes we have, we needed a specific number of additions, multiplications, and subtractions that lead to some time, right? So if you employ bridging, for example, that reduced the time from 5,000 seconds to 700 seconds. So it's a significant performance improvement when we manage to play with the data types that we use to compute the correlations on the data. The other great thing about bridging, I have it, next slide, is that because it reduces the number of operations, since it keeps data in modular arithmetic as much as it can, it leads to high performance by the reduction, but the reduction itself has a side effect of reducing the depth of computation. And reducing the depth gives you the ability to actually go lower in the encryption parameters you need to fit the noise. So less computation, less noise you need, so you can tone down the encryption parameters. So you already have another performance improvement by using smaller polynomials and smaller coefficients. So we see that bridging, without bridging, you couldn't go to do the 14 or 13. With bridging, you could. and we end up with a final performance improvement, then going from 5,000 seconds down to 80 seconds, right? Again, two performance improvements. One is the reduction of operations, means less computation, faster, but less computation means less depth. So less depth means smaller polynomials, so faster as well. So two factors we gain speed up. And the other case study is that was the competition after. We just got a paper accepted in Nature Scientific Reports, which is on cancer type prediction. So the idea is the problem and the objective is similar, right? That we want to understand the prediction of cancer, which is the example I was giving before, that is given somatic mutations. Somatic mutations are mutations. We're born with a DNA that's, the same in the beginning, but then actually our cells mutate, right, all the time. So given our current mutations, we can actually understand where we're heading at. And that, again, the problem is, privacy. You still want the doctor to tell you, be careful, this is coming to you, but you cannot share your genomic data. Here, the problem is different than before because we have really high dimensional data. You have, first of all, many classes of what kind of cancer you can possibly have. And then the input, the SNPs, single nucleotide something that you need to give to the system to get the answer back is actually in the order of thousands. So having so many dimensions of the data makes it impossible to just blindly apply FHE without thinking too much about it. So the solution we have is we try to play with the encoding. For the people who use FHE or try to use FHE, you understand encoding is half of the problem, right? How you actually encode the data properly to be FHE friendly and to be able to compute on it with efficiency. So the data encoding came from biological information that the somatic mutations will kind of encode them in a different way. But the novelty that I can understand is that the new matrix multiplication we have to create in order to be able to perform computation at a higher level. So some results, like the accuracy. So these are the possible types of cancer that that your genome can be classified as having predisposition to: bladder, breast, colon, kidney, so on and so forth. And then here we have classification accuracy because now we do machine learning. State-of-the-art prediction for cancer, even somatic mutations, is machine learning based. So that solution now is an ML solution we employ, and we convert it to private. We do private inference actually with FHE. The results in terms of computation, compared to having a simple, naive matrix multiplication, like template matrix multiplication, having a smarter one that we actually transpose the way we use the data, leads to some performance improvement. At the end, that maybe when you have too many samples, it kind of dissipates, becomes as slow as regular matrix multiplication. But typically, you have the samples. So this is more of a latency problem, not a throughput problem, right? So if you want to do one or two samples, you can do it very quickly. But if you want to do like a lot of samples, like in many thousands together, then you still have to go through all of them one by one. In a way, that exploits matrix multiplication and batching together and bridging actually from before in order to make things very efficient for one patient. But if you still have a lot of patients, you have to sequentially take them through. So at the end, you end up having the same performance as just doing everything with regular parallelism. So we kind of flip the parallelism to be latency-based, not throughput-based. That's why we get improvement in the small ones. That's what the problem was asking us to do, right? What is the inference you can do for one patient in this case? All right, so this kind of concludes the software part, right? We employed some software optimizations in order to be able to improve FHE performance coming from the algorithmic side. Bridging can give you up to 100x, depending on the application that don't benefit at all from bridging. There's some that do. And the matrix multiplication one will also see 100x improvement, mostly in latency and not throughput in this side. So this is the side of software. And again, maybe it's a good time for questions. I see on chat. Or a question here, half arm raised.
Just one question, like bridging requires communication in between?
No. The data type, I mean, it is the compiler does dynamic, well, actually there's dynamic casting. So during execution, the data types are being casted. Like C++, right? You have float cast to int. It's the same idea. Dynamically, you cast a secure int to a secure bool or secure mode. So the framework does that. And the classes, the way it works is that you load our data types as libraries, and the libraries has functions for casting.
Yeah.
So a function is being called to cast between data types.
Okay. So like I'm the client, you're the server. I give you my number encrypted on some mode something, and then you obtain the bit decomposition of that number without interacting with me.
So FHE, it's only the benefit of FHE is a fire and forget application. MPC requires communication, right? FHE is fire and forget.
Yeah.
You just send it, forget about it.
It's for this specific operation.
It happens in the server side. There's no communication for conversions. If you were to communicate, it will be much cheaper, right? Computation, because you send it back and you convert for me, or can you do this for me? But we don't do MPC. I'm not an expert, or I don't know even much about MPC. But I know the communication cost is the performance bottleneck, right? FHE, we use it as a fire forget kind of a thing. You just send the data, everything happens there. No communication. You just get the result back. Performance, I mean, depends on the application, right? If you were to do, for example, secret sharing, then that can have, for some application, much better performance than FHE. So depends on your computational complexity, your communication complexity. It's the trade-offs here.
Yeah, it's just a curiosity about how the conversion works, because I'm not aware how to do it without asking me to decrypt something.
No, there's no decryption happening anywhere. So the algorithm itself includes the casting as part of the algorithm, the cast between data types.
Can you comment a bit on the underlying formulation for the table you have with the time source?
For bridging?
Yes. Was there any sort of parallelism being used?
Yes, batching is also used heavily. So batching, you have to use it to make anything practical, right? So batching is used a lot. So we kind of try to use all the slots. But other than that, becomes an algorithm change.
For both, or using some sort of parallelism?
Yes.
At instruction level and also thread level?
At the encoding level. So when you put a plain text into ciphertext, you actually put a lot of plain text. So every slot in some way would have a different thing we want to compute on. So there's definitely the data level paradigm at the batching level in both cases. Yes.
Can we use current hardware accelerators like GPUs to perform or improve the performance of FHE?
Second part. Give me a few minutes. Yes.
Just one thing. So the switching between the data types now is then performed homomorphically.
Correct.
Yes.
Yes.
So it has to be secure. And is the security of this operation like self-standing, or does it rely on the security of addition, multiplication, and division?
That's a very good question. So the casting happens using existing FHE operations.
Okay.
So you do additional multiplication. Same with bootstrapping, right?
Okay.
Bootstrapping, yeah, so nothing changes. Additional multiplications are applied.
And how does that circuit looks like? The circuit that does the conversion from.
So it's not a circuit, it's code that the conversion, well, I mean, depends on the conversion, right? I'd be happy to discuss the technical details. So depending on whether you do either a bit expansion.
How do you do that bit expansion without having to decrypt anything and just
Homomorphically.
Yeah.
It's like decrypting homomorphically, right? Bootstrapping decrypts homomorphically.
Yeah.
And refreshes the noise. So same thing, you compute things homomorphically. We can discuss later the technical details. And also all right. To answer your question, I have slides prepared for you. So the hardware-based acceleration. So hardware, we need to see what FHE really is in its primitives, right? So the most popular FHE schemes, they rely on the similar hardness assumption, which is based on the problem of ring learning with errors. So in this problem, a plain text becomes a polynomial, right? That's how it works. And a polynomial in a ring, and the typical sizes of the polynomials depend on two things: security level you want and the noise budget you need, right? So those two factors are defining how big your polynomial should be. And its size, it's a size of polynomial, there are two things. One is the degree, and one is the coefficient size. So here n refers to the degree of the polynomial, right? And any practical starts from 4,000, right? Well, even that is too small to fit. That fits on application much. So we start typically from here, have any serious application in place. And then depending on the security level you want, you have some correspondence in what the coefficient size at minimum should be. So here for 120-bit security level, and if that's the depth of computation you need, the coefficients have to be as big as 113 bits. If you do 8,000 degree polynomial, it has to be 222, 16,000 for 40, and so on and so forth. So here we're talking about essentially trying to create hardware to compute very, very, very big polynomials. And again, there are two problems. One, we have polynomials. And the second, the native word sizes we have, they're not native to the computer. The computer computes 64 bits easily, but 128 to 56, it has to do magic, right? Because it doesn't fit in a register. So to be able to do more than 64, you have to introduce GMP, or you have to introduce some library to compute on things more than 64 bits natively. I have the example of CryptoNet. It was one of the first papers that came that did private inference, where they showed a very small network that did very basic and niche stuff. And CryptoNet had a lot of ideas in place. One was to also approximate the activation functions. So they're not exact, they're approximations. So they convert activation functions to be non-linear, right? But they made them linear, which is weird because this is not machine learning anymore. If everything is linear in your inference, it's just an algorithm. But they did that as a trick, and they proved that they can do the same accuracy with their modified activation functions and the modified network they showed. It had a degree polynomial of 4,000, and it was 4,000, then so correspondingly to 120-bit security, you have 109 bits ciphertext modules. So that creates that very small thing. Actually, that's a very tiny polynomial from what we see. It would take 55 kilobytes to be stored and 55 kilobytes to be computed on, right? And a native computer data type is 64 bits. Here, our data type is 55 kilobytes at its smallest version. So imagine how, as you expand that, becomes megabytes that you need to do for one plain text. So the hardware we need to design needs to support two things, right? One is polynomial operations, because we don't compute on big numbers, we compute on polynomials. So we need to work with polynomials, and every paper you have read so far has NTT as part of the processing. Why? Well, because regular polynomial multiplication school book is n squared complexity. NTT brings it to n log n, so that's why we love it. So every polynomial multiplication in modern literature is entity-based. Same, our work is the same. And when you do NTT, right, at the heart of the computation, you have the computation of the coefficients. The coefficients are big, right? It can be at least 128, it can be 256, it can be 512, that are not, you cannot give them to the NU of the CPU to do a 500-bit computation. So to be able to perform more than 128 bits, you can do two things. One is to actually use an external library that has arbitrary precision classes. So you have 500 bits as a class, and then internally the class does all the computation needed to do the addition or multiplication of those coefficients. And that's what software does. And what we see a lot in hardware is the use of the residue number system. So in a way, you can take the bit coefficients, you can split them in towers that are of a size that are native to CPU. So you can split them, you can take prime moduli in order to have the 256-bit number split into 30-bit numbers, many of them, right? The division of 1028 by how many you want to have, and then by 30 to understand how many you need. And then now, so you have only 30-bit numbers, many of them though, but they're 30-bit, you can compute them natively in the CPU. So RNS is the other way of being able to perform computation. So when we discuss hardware, we need to do both to some extent, right? We need to do polynomial operations, and we have to do the coefficient operations. So this is how I view the hardware stack. So at the heart of the computation, there's modular multiplier. And then you take the modular multipliers, all of them, and you do polynomial operations. NDT, inverse NDT, the actual Hadamard element-wise multiplication. And then with the polynomial operations, you move to the ciphertext level, where you have key switching, modular switching, and the operations that you operate on polynomials, but at a higher level than the polynomials. So some work we've done, on these fronts. Actually, that's part of the DARPA program I participate. The first phase was to explore the modular multiplication landscape, because there are many ways you can do modular multiplication, right? There's not only one way. There are many algorithms. So we wanted to explore what is the most efficient algorithm for modular multiplication in the context of FHE. What is the context of FHE? There are going to be many multipliers. They're going to be a specific size, 128, 256, or you need flexibility between sizes. You need low power. Why? Because there are many of them on chip. So you have to be very careful about power, otherwise your chip will melt if all of them work together and they're very power hungry. So all these things make the problem unique to FHE. So we did an exploration phase with DARPA for 15 months to understand what is the best modular multiplier that can be employed. So the paper is accepted. I think we'll have it maybe an archive or not. I can send it to you. So we'll be presented in a few months. But I can share all the data anyway. We have the repository open source there. So modular multiplication can be seen in two big groups. One is you operate on bits in parallel, or you operate bits serially, one by one, right? By themselves, the classes, you understand they have different properties. So the bit serial probably is smaller and slower. The bit parallel is faster and bigger. We can see that by, again, how the chunk of data being processed as a unit. But what we're trying to understand is the ratio between area and performance, right? We want the smaller area for the biggest performance. That can come from both categories, right? Maybe that's so efficient that the fact it is slow, it's overtaken by how small they are. Or the area product ratio is better for the big parallel ones, right? So we did the exploration using some algorithms, interleave and Montgomery for bit serial. Montgomery can also be used with bigger chunks, and the Barrett reduction and the Barrett multiplier is also what we tested a lot for performance, understanding performance. Something that the only remaining piece here is MC label. I should have the label here. That stands for modulus constraint. So these are modular multipliers, right? The modulus in the generic form of multiplier can be any size, any form. However, if you restrict the form of the modulus to be, for example, having a lot of zeros, with something you can do because you pick the moduli yourself, right? When you create your encryption and you do your RNS, you pick the moduli yourself. So you can pick the moduli to be of a specific form. And doing that, you can actually reduce the hardware area a lot. So if you constrain the type of the modulus you're employing, then you have a lot of area reduction. However, now you don't have a generic multiplier anymore. However, if you only use for FHE, what do you care, right? You do FHE computation, you can do the modulus constraint. But we explore it a bit differently from the regular ones because you may want the regular ones to be in place too. So very quickly going over the results again, I think I'd like I'm doing more breadth than depth, but everything I say is a paper, so you can find more information in the papers. You see the different multipliers and different bit sizes from 32 to 6, and you see the trends, right? So the two distinct clusters. The cluster here is the bit parallel, and the cluster here is the bit serial. Not unexpected, right? Small and slow, big and fast, right? We kind of see that actually coming. However, if you see the parity lines here, at the end, the bit parallel are better in performance, are better for the throughput for the area. So what you get for what you pay is a better trade-off for the bit parallel compared to the bit serial. That's one big observation we make. The other thing is what between the bit parallels, right? What seems to be the case? Well, the Montgomery modulus constraint, actually that's what the F1 paper is using, seems to be the highest performance, followed by the Barrett multiplier. And we employed the Barrett actually ourselves because of other reasons that I'll discuss. So that's in terms of throughput for the area.
Is frequency normalized for both?
Frequency is fixed for every frequency is fixed at 1 gigahertz for every design. That's a very good question, because that's the DARPA program said 1 gigahertz clock, so it has to run at the same speed. Bit serial are easy, right? Because they're already slow, so they can do they have a short critical path, but that's more challenging, and we need pipeline to achieve. So what's hiding here is that many of these designs are multi-stage pipelines. With a Barrett to reach 13 stages, to reach 1 gigahertz, we have 13 stages. So the latency is 13 cycles in this case, but it's pipeline, so you keep feeding. Ashraf knows better all these things that we did for the previous chip. All right. And other thing that's important, I said, is power. So I have, again, throughput for the power budget need. Same clusters. The smaller ones, we expect them to need less power. The big ones need more power. So you see that they're getting closer in how they perform this power. Till here, you see that the high performance designs would need a higher power budget compared to there. And you have to take that into account when you do the whole thing, right? Power is going to be, well, the two big problems with designing hardware for FHE. One is data movement, the other one is power. Because what we compute on is cryptography. Cryptography has 50% switching, right? Pretty much. So you cannot really have patterns that half of the chip is not used now, the other half is used. Everything will be used all the time. Having these patterns coming into your chip makes your chip very prone to having hotspots. And having hotspots will eventually may lead to higher than expected thermal properties that could lead to damage in silicon. So power has to be taken into consideration very early in the design stage. That's with hardware. Moving on to, with the modular multiplier. And then we took the knowledge from the exploration, the design space exploration of the modular multiplication, and moved up to trying to see how we can actually put a polynomial operation processor. And this is we got accept the date. It's going to be presented in April. The processor we call it Coffee, because we like coffee a lot. Well, that's a fancy name. We like it a lot. Which is a coprocessor for fully homomorphic encryption and execution. And actually, I did bring a chip. You know, you want to do a demo to impress people, right? But it's not a demo, it's more the actual chip. But I wanted to bring it and leave it here in case you're interested in, checking its API and everything. So that the chip we fabricated, all the chip is this thing. The surrounding is a board to interface with it. So it's pretty small, as you can see. It's 15 mm square, built at global foundries, 55 nanometers, around 250 megahertz. PLL, which hasn't been working yet, but we're trying to see how to make it work. 100 megahertz with external clock input. It works, everything works except for SPI and the PLL. The rest are working. But this is the fate of fabrication, right? I mean, we're lucky we got even that working, that part that works now. But it's an academic prototype, to the best of my knowledge, the first of its kind to be fabricated and proven in silicon. So what Coffee is internally, as you understand, we're talking about big polynomials, right? So they have to be stored. Most of the chip is memory to be storing polynomials. So a lot of restaurants will have different banks because every bank will contain one polynomial. We need two to load for the operation, one to store the result, and then we have two factors. So some of the SRAMs are containing the two factors for the entity. So this is a lot, the design is driven by polynomial multiplication a lot. So there are a lot of memories. We have our modular multiplier pool. As I said, we pick the Barrett multiplier from the exploration I showed you before. There's some controllers. There's the ARM Cortex-0. We have to control how things move around. But the main data movement happened by a dedicated controller. So NTT is mostly data movement. So the data movement happens by a dedicated design module. Some other things, communication interface, like your SPI doesn't work, unfortunately. This doesn't work either, but everything else works in the fabricated version. In simulation, everything works, right? Fabrication is the moment of truth. As I said, 55 nanometers, global foundries, 15 mm square. It can do 8,000 degree polynomials. It's pretty small, but that's the budget we have. We couldn't, it's already very expensive to do that. So we couldn't do something bigger than this, but we have RNS, so we can split into 120 coefficients to support. That's the setup. I'll tell you. So the Chiara, when he came, feel free to come. Actually, gave you one copy. You can keep it if you want to use it. We can show you how to interface with it. So maybe it can be useful to you if you do API developments or you want to understand how hardware works, interfaces. Feel free, and we can support its integration in here. And you already have an expert who can help you a lot with integrating here.
Can you comment on codes for ARM?
On what?
On the ARM part?
So this is a very really tiny controller, right? And
Yes.
many times we need to have, for example, reset and clearing the memory, setting up the configuration registers. So we have the Cortex laser. It's like a tiny brain that helps us do anything.
Why not the RISC-V?
Well, I'm not sure how big is RISC-V. This is extremely small.
Yeah, very small. RISC-V.
I don't know. That's what ARM gave us as a macro.
That's
Yeah,
it.
they gave it to us as a macro, right?
Okay.
So just put it in, and if it's a macro, it already works, right? So you have guarantees about its users. If you want to do your RISC-V backend from the beginning, then I'm not sure how successful it would have been. But again, it's a very tiny macro. We add it, and more for us, it's easy to program in ARM assembly too. But you're right. I mean, it could be any processor, can be RISC-V too.
How many modules you support? Different?
All of them. This is not a constrained one. We have a regular Barrett multiplier. We didn't want to constrain, but if we had, we would reduce the multiplier size. We didn't. Well, actually, honestly, we didn't know about the technique at the time when it was sent for fabrication. But it took us a year to take it back. So by the time we knew that it was too late, the new one would have the constrained one. That's the API of copy. So you see just polynomial operations, right? Is entity inverse entity, point-wise addition, point-wise multiplication. In a way, a ciphertext multiplication is entity, point-wise multiplication, inverse entity, right? So we have this as an API. We have constant multiplication that's also heavily used in machine learning, because if you imply that the server model is in plain text, most of the operations are actually between plain text and ciphertext. So the multiplication by constant is very useful for the machine learning applications. And auxiliary functions for copying between memories and bit reverse, because we don't know the format of the data coming in. Comparison. So comparison here, honestly, are a bit contrived in order to make the paper be accepted somewhere, because the chip is so small, it cannot be faster than a CPU. Why? Well, Intel's processors like a million times bigger than what we have. So in absolute numbers, actually, we're slightly faster, which doesn't say anything, right? Slightly faster will be, I don't care. It should be CPU based. So we have kind of try to make some comparisons with normalizing. So coffee is a couple of orders or a couple of orders might be faster for some benchmarks. But again, honestly speaking, the performance is not really what makes this distinct, right? And the fact that it exists is what makes it distinct. So to make some comparisons, because reviewers keep asking for comparisons, we normalized as much as we can for the area. So we try to see for the frequency we had, for the area we had, how much area we need. Ours is pretty small compared to F1 at the time, was 150 mm square. And then we have FPGA comparisons, but they're not really fair because an FPGA is an ASIC that's custom built to do something very specific. So all these comparisons are all questionable to some extent, but they give you some idea of where we stand, but it should not be taken at face value.
The Roy paper is probably some SHE, right? It's not fully FHE.
Probably. I think so. Yeah. So Joy did work a lot on somewhat homomorphic. That's true, actually. Well, I think most people do some homomorphic implying there's no bootstrapping. So different ways to see the problem, what is somewhat homomorphically is new. But there's definitely no bootstrapping here. Bootstrapping, we don't see many papers bootstrapping at PTA. Most of them do somewhat. So they assume a limit in the budget, and that's it. They design for that. All right, and the last thing, so we can conclude the talk, is current work we have, which will go again an upper level in the stack. This is work in progress. We haven't taken out something yet, partly because the backend person left and we have to replace. So the new person arrived, so we can resume the backend process and fabricate the next iteration of coffee, which is a ring processing unit. So we're kind of going the higher up in the stack, where we're trying to have now ciphertext processing, right? Not just polynomials. So we have our polynomial processor that you can do NDT and everything, but now we're talking about high-level structures such as vectors. So everything now is a vector, and we have vector memory, and we have our lanes that within that we have the computational units I showed before. Right? So coffee that you saw before is kind of hiding here as a lane that takes a polynomial and does operations, and then things move around a lot. Entity can also be seen at the crossbars because data moves between lanes for processing. So this what we have now is mostly an architectural exploration. This is not the final diagram. It's missing a lot of things that are needed for the final fabrication. However, what we do is exploring the trade-offs between adding lanes and adding banks, right? So you can add more memory, but you don't have processing for it, it's useless. You can add more processing, you have memory for it, it's useless. So there's a trade-off to be found between how much memory, how much computation you put. So we did some kind of exploration at Pareto front. We're trying to identify about how varying the number of lanes and the number of memory banks gives different runtime improvements for the area, right? I mean, apparently, it's faster when you spend more, right? And it's slower when you spend less. But there's a Pareto front that is being found, right? So you can see somehow the trade-offs, and some designs are definitely worse. Some designs are on the front. So if you were to do some configuration, you wouldn't pick this one that I don't know, it's probably 816, and you do 864. Or if you can spend, let's say you have 16 mm square, you draw the line and you see what you can afford 64 lanes, 128 banks. So this gives you an idea for the area you have, what is the optimal configuration of memory and computational units you should put in your FHE ASIC.
You're using the same entity always?
Yes, actually what's missing from the discussion is we use Spiral, if you know it, that creates entity for the hardware. Right. So Spiral is hiding somewhere. Spiral is in our team. Yeah, right. Yeah, we work with them in the Delta project together. And then that's another presentation of, again, understanding the trade-offs, right, and finding the optimal points. Actually, this is what we're fabricating now, 128, 128. That's going to be the next chip. We found it to be the optimal configuration. To conclude, very high level, a lot of work needs to be done at crypto level, at the software level, at the hardware level, but they have to be done somehow together. Ideally, I don't have it yet, but we're moving towards way a co-design process will be the ideal environment for maximum performance improvement. And to conclude everything, all the things are papers that are published or in progress that I can share with you. And then we have GitHub repositories, bridging and the IFLI framework. Compiling is already there. It's many years now. The application of cancer prediction, you can find it here, and Coffee, the design files. I'm not sure if they're up yet. Probably will wait for publication to be official. To upload it, that should be April. So when we'll put the designs up. I have to mention acknowledgement. The whole work has been funded by DARPA. I will work actually with Duality towards this. Duality is a league, and NYU, CMU, and USC are working with Duality towards building at the end a big FHE accelerator. And with that, open to questions. And yes. Yes.
Like your chip is capable of doing 8,193 polygons. Can you give me any rough figure how expensive it is going to be if you move to 16,368 polygon?
So
And how about the size as well? 15 millimeters.
I'll just give you estimations. That's a very good question. Actually, I asked my team to be able to answer it, right? Because in some way you can look at this as a prototype. And then you can choose a number, you can get the area back. So we kind of moved out of Coffee for this, and we moved towards that way of exploring, right? And we have the area for what we get. So we haven't done it for Coffee, we're doing it for the new design that we say, okay, given that many units, that much polynomial support, this is the area you need. But for Coffee specifically, the dominant factor, I don't have the pie chart, is the memories. So doubling the polynomial size doubles the memories. Memories, I think, to the best of my understanding, is 7 mm square. You remember, Ashraf? 7. So most of the chip is memory. So doubling that will give you 7 mm extra already. Doubling the ALU shouldn't be that bad. So I'd say 15 would go, very roughly, would go to 25. Very roughly. It's not exponential, but it's, well, in price, maybe exponential. what you pay for, there's a cutoff that then they charge you way more if you go to a big chip.
Why I'm asking about 16,000 because whenever I do any kind of a chip,
I agree with you.
I try to be in 8,000, but I think I have to go in 16,000.
I fully agree. That's why we're scaling up. The next one should be more than 16, I think. I think we'll do 32,000 in the next chip. But it's also smaller process. We're doing TSMC 22. So there's more area to use.
May I know how expensive? I want to buy
Coffee, this fabrication costs $80,000. You change your mind?
But you got the university price. We are paying way more than that.
That's true.
That's because it was 55.
Yeah,
Wow.
it was an older, it's what we had at the time because of the NDAs and this stuff, right? It's annoying. Now we move to TSMC. I don't think we'll get any discounts. TSMC 22. I think that's the same, right? 22, 28 are the same pretty much.
We are going on 28.
We are GF.
Yeah.
Now with TSMC because of use, it's most of it is hard to work with. So we're actually changing those providers. Yes.
The way I see Coffee, it's like targeting more lower power and kind of design. So
Yeah.
can you comment a bit on your view on like tightly coupled accelerators versus loosely coupled?
So we're still on the exploration phase on that, right? The SRPU thing, actually, it's not really a unit, it's a simulator that you feed it stuff and gives you back performance outputs. Honestly, I don't have the answer, and more honestly, I'm not an expert at that level. Because now we start talking about key switching, talking about all these, the algorithms that are heavy on using memory from all over the ciphertext. So it becomes more of you have local data when you need. So that has to be understood, and that's what we're trying to do now. So key suites, the key suites matrix depends on your whether you do RNS or not, and how much RNS you do. Right? If you don't do RNS, key suites matrix is actually very small. Right? If you do 512 bits, regular coefficient, you don't have many things, right? But everybody does RNS, so it makes the memory big. But if you don't do much RNS, there's a trade-off to be found on how much RNS makes you spend for what you get back. So we're currently in the stage we're exploring that we'll see, okay, since it's ASIC, we can do 500-bit coefficients, right? Why do 32 bits? All the papers F1, they all do 32 bits because I think they're more used to 32-bit data types. And indeed, the multipliers can be more efficient when they're small. Still, RNS gives you problems at a higher level, including key switching. So there's a balance to be found on how much RNS should be added for what you lose by the inefficiency. So there's an efficiency of the multiplier as you increase the bit size, but the increase in the key matrix, the key switch matrix you have, you need more data movement. So there's some sweet spot there found. So I cannot give you a solid answer yet, hopefully in a few months.
Well, more comparisons between instead of just using RNS pipeline, which is the trivial solution to the
pipeline. We have actually the ISQED paper. Oops, I'm running low, but anyway, this will die. The ISQED paper has the same all this exploration with pipeline stages too. So you see for different pipeline stages how the multipliers kind of respond to. However, pipelining is not an idea that can be employed easily past the functional units. The rest of the chip is memory that moves around. So in that context, pipeline is meaningful as long as you can feed it and your initiation interval starts playing a big role. How fast can you bring things to the functional units? So the pipeline is relevant to, we always try, another question is in all these designs have initiation interval of 1. So they can take one operand in every cycle. That makes a more fair comparison between the algorithms. And we want them to be able to be fed one operand per cycle because we kind of hope that the multipliers won't be the bottleneck. However, what seems to be the bottleneck is data doesn't arrive in one cycle. It needs more. That we're still exploring.
So usually in crypto, like when we implement finite field multipliers, so we somehow relax the constraints on the coefficients.
On which ones?
You can relax the coefficients. Basically, for example, I see here the coefficients are like genuine. For example, if it is like low heavy weight, it somehow right?
You mean the actual values of the coefficient or the modulus?
No, the values.
I'm not sure if that can be done. I think you should be able to support any arbitrary value as a coefficient value.
Yeah, so right now it supports arbitrary.
Yes.
Let's say the coefficients, I know that having weight is, let's say,
If you knew that, then yes, you could have definitely a more efficient design, 100%. But I don't think that's possible in FHE. I think that's impossible theoretically, but again, I'm not the right person to answer that. That's my understanding, that coefficient should be any number. Modulus is chosen because the coefficient is the input. Input can be anything. But the modulus is just the setup of the crypto system. But you can set it up any way you want.
So you can still encode or decode the coefficient. Those quantum they do them.
yeah, but we make the weight is
No, but you can keep it like to put a round, let's say, on -3 to 3. You can map it to that.
There are also some questions in the chat.
Yes. Second question, what is the meaning to use HC at some point if you need to decrypt anyway to use the information so you expose the info? Is the less entry point to attack? It's a good question. So it depends on you look at the problem as secure outsourcing or not, right? Indeed, at some point you have to have meaning of the result. So the idea of your computer being FHE encrypted is probably meaningless, right? But it's more in the context of secure outsourcing or private outsourcing when you send the data to a laboratory and it's being processed and get the data back. I don't see it meaningful being FHE encrypted in your computer, since you still have to be able to use it. And your other question, GPCFG, that's the general purpose configuration registers. And they're used to set up things like what is the coefficient size, what is the algorithm for the entity. We have a few options that need to be set up. That's what the ARM core actually is doing, in order for the chip to work properly. It's like initialization registers, configuration registers.
And also follow up on the homomorphic casting.
Yes.
So since casting is quite a low level operation, if we were like, and this casting, the overhead in this casting is pretty much what determines how many times you can switch. You know, because then it goes up very fast, and it depends on the addition and the multiplication. You know? So I wanted to know if you look into a different way of doing this homomorphic casting that doesn't directly involve, doesn't depend on addition and multiplication, if there might be an alternative list that maybe makes everything.
These are the two operations you have, right? Addition, multiplication, you don't have any other operations. Well,
well, that's what I'm asking. If you ever thought of defining?
No, because then it changes the crypto system, right? If you could do other operations, I don't think you can do them homomorphically. When we take the FHE scheme, it only gives us a val add, a val must. These are the two operations we have. We can't get anything else.
Yeah, but I mean, okay.
Unless you decrypt, for example,
you
can do other magic, right? If you can decrypt, you can do whatever you want.
Yeah, I mean, the point is you define the addition and the multiplication in a homomorphic way, and then from those you build everything else.
No,
okay.
We actually use the FHE addition multiplication.
Yes, that's what
it's not. We didn't define them homomorphically. They exist as part of the API, right? So you set up the crypto system, you put the key generation, you do the encryption, and then you only have two operations you can use: addition, multiplication.